we can plot H versus W. So on the vertical axis, we have H, the probability of the husband. And since it's a probability, it has to lie between 0 and 1. On the horizontal axis, we have the wife's probability of going to the ballet, which also lies between 0 and 1. And first of all, notice when H is equal to 1/3, W, the probability of the wife going to the ballet, W could lie anywhere between 0 and 1. It could be any value. When H is less than 1/3, the wife's probability should be below 1/3 as well, right? Any value below 1/3 up to 0. To maximize her payoff, she should set it equal to 0. When H is greater than 1/3, the wife's probability W should also be greater than 1/3. It should, in order to maximize her payoff, it should be 1. So when H is greater than 1/3, the wife's probability W should be 1/3, between 1/3 to 1. And when we mark these probabilities out with this black bold line, we have the wife's best response function. Now, recall that the expected payoff of the husband is equal to 2 minus 2h minus 2w plus 3hw. We can repeat the exercise that we just did for the husband. We can check out his best response when w is equal to 2/3, when w is less than 2/3, and when w is greater than 2/3. And after that, we can plot his best response function on the diagram above. Why 2/3? Because 2/3 is a special value of W, which causes H to vanish. So in this expression, if you replace this W by 2/3, you will get 2H. So you have plus 2H and minus 2H. So the H vanishes. And 2 into 2/3 is 4/3. 2 minus 4/3 will give you, husband, the expected payoff of the husband as equal to 2/3. So let's repeat this. Let's plot the husband's best response function on this diagram. When we do it, this is what we get. So again, 2/3 is a critical value for W, for the husband. When W is less than 2/3, the husband's probabilities should also be less than 2/3 and should be 0. Okay? When the wife's probability is equal to 2/3, exactly equal to 2/3, the husband could set any probability in between 2/3 and 1. Any probability. Between 0 and 1, I beg your pardon, between 0 and 1, when W is equal to 2/3. And when W is equal to, or sorry, when W is greater than 2/3, the husband should set a probability between 2/3 and 1. Okay, so this dashed line, right? So once again, when W is exactly equal to 2/3, the husband can set any probability between 0 and 1. So this is the vertical section. When W is less than 2/3, the husband should set a probability of less than 2/3 as well, 0. So this is the horizontal section. And when W is greater than 2/3, the husband should set a probability anywhere between 2/3 and 1, which is this horizontal dashed line. Now, where the two best response functions intersect give us the Nash equilibria E1 and E2, where H and W are both 0, is a Nash equilibria. So at E1, H equal to H equal to 0 and W is equal to 0. That means that 1 minus H and 1 minus W are equal to 1. What is 1 minus H? 1 minus H is the probability of the husband going to the boxing match. What is 1 minus W? 1 minus W is the probability of the wife going to the boxing match. So when H and W are 0, 1 minus H and 1 minus W are both 1. So if both the husband and the wife go to the boxing match, that represents a Nash equilibrium in pure strategies. If you remember, when we figured out the Nash equilibrium in pure strategies, boxing was a pure strategy Nash equilibrium. At E2, both H and W are equal to 1. So both husband and wife end up at the ballet. That too, so ballet, that too represents a Nash equilibrium in pure strategies. At point E3, where the two step functions intersect, you have H is equal to 1/3 and W is equal to 2/3. And that represents a mixed strategy Nash equilibrium, where the wife is going to the ballet 2/3 of the time, and the husband is going to the ballet 1/3 of the time. Now, we figured out the values of H and W by calculating the expected value of the husband and the wife given both their probability sets. There are actually two other approaches to finding out the optimal values of W and H. First, we can calculate the expected payoffs for the wife separately for when she goes to ballet and for when she goes to boxing. So if the wife goes to ballet only, given the husband's probabilities H and 1 minus H, then her expected payoff is H times 2 plus 1 minus H times 0, and that is equal to 2H. The wife's expected payoff when she only goes to boxing, given the husband's probabilities H and 1 minus H, is H times 0 plus 1 minus H times 1, which when simplified is 1 minus H. Notice, and this is a thumb rule for calculating expected payoffs, H is the probability of the husband, 2 is the payoff of the wife. So always when you're calculating expected payoffs like this, use your own payoff, but the other's probability. Okay, so the thumb rule is my payoff, but the other's probability. So 2 and 0 represent the wife's payoffs, but H and 1 minus H represent the husband's probabilities. Again, 0 and 1 represent the wife's payoffs, but H and 1 minus H represents the other person, the husband's probabilities. And when you've simplified, you get 2H and 1 minus H. If the wife is indifferent between the two strategies, boxing and ballet, you equate the two values. So you get 2H is equal to 1 minus H, or H star, your equilibrium value of H, is equal to 1/3. So what have we figured out? We have figured out H star. That is the probability of the husband going to the ballet. This is because the wife's expected payoffs depend on H and not W. So let's calculate the husband's expected payoffs for going to ballet and boxing separately to figure out W star. So once again, use your own payoff, but the other's probability, right? So that's the thumb rule. So the expected payoff of the husband of going to ballet is W times 1. 1 is the husband's payoff, W is the wife's probability, plus 1 minus W times 0, and that is equal to W. The expected payoff of the husband of going to boxing, given the wife's probabilities, is W times 0. 0 is the husband's payoff, plus 1 minus W times 2, which is the husband's payoff, and that's equal to 2 minus 2W. If the husband is indifferent between the two, you equate them. So W is equal to 2 minus W, or W star is equal to 2/3. So this is the second way of figuring out your optimal values of H and W. This is maybe an easier way of doing so than calculating the expected value of the entire probability set, but it is up to you. It is up to you. Now, which one you use. Now, the final approach involves optimization of the expected payoffs with respect to H or W. Now, continue to remember that the wife's payoffs depend on H and the husband's payoff depends on W. So for the final approach, you need to calculate the original expected payoff. So you need to calculate this expression, which we already have done. So that is equal to 1 minus H minus W plus 3HW. And the wife maximizes her expected payoff with respect to H because her best responses depend on H. So del U by del H is equal to -1 plus 3W. You set it equal to 0 because we are optimizing or maximizing. And from here, you can directly calculate that W star is equal to 1/3. So similarly, we had already calculated the expected payoff of the husband for given the probabilities of himself and his wife as 2 minus 2H minus 2W plus 3HW. And the husband would maximize his payoff with respect to W, right? The wife's probability. So del U by del W is equal to -2 plus 3H, and you set it equal to 0. And from here, H star is equal to 2 by 3. So, if you are going to adopt this calculus-based approach, you need to calculate the expected payoff for the entire probability set like we had done earlier. So of the three approaches, you choose which one is most easy or most convenient for yourself. So I'm going to stop the video here.